I think the syllabus for your particular class, which is the semester system, the old semester system, does not contain a lot on linear operators. But I think it would be a pity if we didn't do enough on linear operators for you to be able to understand the language of quantum mechanics next semester. So I'm going to spend a bit of time talking about linear operators. And in fact, this is when the course will get kind of interesting for you, because you'll begin to see connections between what we've done so far and what we did in the second semester when solving systems of differential equations. If you remember, one of the things we did when solving systems of differential equations was to write them as in the form of some operator acting on a vector equal to a matrix operating on a vector. And we all learned how to find eigenvalues, eigenvectors of these matrices and solve the problem using those methods. And we found that the solutions we obtained using these new methods were the same as those obtained using the earlier methods, but it was a completely different way of doing things. And I must tell you, I don't know if I did at that time, that I was very pleased at how well a lot of you seemed to learn the idea of eigenvectors and eigenvalues, even though it was not in the course. Okay, I found that in general, the class seemed to have a better appreciation of those things that are outside the course than of those things that are in the course. Okay? So maybe that's the secret. It will only be things that are outside. Anyway, so I got the feeling that you enjoyed doing eigenvalues and eigenvectors. So we'll have more enjoyment of this kind in the next couple of weeks. Okay? And so you're already familiar with the idea of linear operators. We're just going to sort of put this idea in the context of vector spaces. Whereas earlier we sort of just talked about a linear operator, now it will be a linear operator on a vector space. So the definition of a linear operator is very simple. It's suppose you have a vector space V. We'll be talking only about finite dimensional vector spaces. Okay. It turns out that many of the results we obtain for finite dimensional vector spaces can be simply taken over to infinite dimensional vector spaces, though that needs to be done with care, okay? Because some things don't hold when you go to infinite dimensional vector spaces. So it turns out that in quantum mechanics, we can often use many of the results for finite dimensional vector spaces in the case of infinite dimensional vector spaces. So you have a vector space V, and I'll be using, if I can bring myself to draw this kind of special V, and the terminology used in Shankar seems to be this to the power n, meaning that it's an n-dimensional vector space. So you have some element of this vector space, okay? And we'll be using the ket, let us say. This vector is some vector in this vector space. And a linear operator is something that when it acts on this vector space, on this vector in this vector space, takes it to another vector. It's as simple as that. But why we call it linear will become apparent in a couple of minutes. Now, this vector W could be a member of some other vector space. But it turns out that the case we'll be interested in is where the linear operator acting on a vector in a vector space produces another vector in the same vector space. Okay? In that case, we call it a linear operator on that vector space. So in general, but come in. You might often find that W belongs to a subspace of the original vector space, but that doesn't stop it in any way from, that still gives it full membership of the original vector space. Can anyone think of some operators that you have come across in the past which perform this kind of operation? Rotation is something that's very obvious. Okay? You take a position vector, okay, and you apply a rotation operation on it. It gets turned to another vector, and that vector is also a member of the same vector space. Anything else? See, here's how to get new ideas. Okay, one of the ways. It's a little like analytic continuation. Okay? You go to the edge of your idea and you try to see if there are other possible ideas that can be reached from this original idea. When you think of a rotation operator, okay, you have the operation of rotation. So in other words, it's very easy for you to imagine the operation of rotation without attributing any kind of structure to this operation. Something rotates. But you also know, you're all very familiar with the idea that a rotation operator can be described by a matrix, right? So what does that suggest to you? That perhaps the action of other matrices also is like that of a linear operator. In fact, we will find that matrices are sort of the ultimate way of, the most common way of representing operators. Okay? Matrices, we will represent operators as matrices. We'll come to that later. Okay. Anything else? Something that you've seen but you may not think of in this, may not immediately come to your mind. Differentiation. And somehow we've never thought of differentiation as a linear operator. You have sort of been introduced to this idea because when we were talking about Green's functions and things like that in semester 2, I did every once in a while write your linear differential equation as some curly L times acting on something. Okay? And I kept saying that, the solution to the, when you're looking for the solution to the differential equation, you're essentially looking for the operation you're examining the operation of this operator on something. So you begin to understand that differentiation is a linear operator. Now that we have some idea of vector spaces, let's just look at it a little more carefully. Okay? Let's say I have a space of all polynomials up to degree 3. As Saurabh pointed out the other day, I missed this qualification. It should be up to degree 3. Okay? All polynomials up to degree 3. Okay? And let us say that we have some polynomial. Let's say A0 plus A1x plus A2x squared plus A3x cubed. I got the feeling that the other day I said that the dimension of this vector space is 3. It's not 3. It's obviously 4. Because you need 1x squared, x cubed as the basis. Okay, so you need at least these 4. So this is what's called a standard basis. Okay, we consider other bases as well for the infinite polynomial. Okay, I differentiate this. Okay. If I differentiate this, so this is some p x. So dp dx, it takes me to a1 plus 2a2x plus 3a3. Okay? X. So the original polynomial in my representation of the, what is the vector representation of this? A0. And this one is A1, 2A2, 3A3. It's also a member of the same vector space. So the action of differentiation. And You might even begin to have other ideas like how I might represent this operation using a matrix and so on. But we will not immediately explore that idea. We will explore that idea later. Let's just go back to the fundamental definition of the vector space and make it slightly clear. Why it's called a linear operator and so on. Okay, so what would we want if we want to call it a linear operator? Let's extract, as we did in the case of vectors themselves, properties from examples that we're already familiar with. And now I've given you these examples, you're familiar with them. Okay. So I have some linear operator. Let me use the terminology given in Shankar. He's used uppercase Greek letters for operators, at least in this chapter. Later on, I don't think he can. So I have list the properties. So if I have the operator acting not on the original vector, but some scalar times the original operator, we all know this. Okay? This is just going to be. We all know this because essentially what we are writing down are things that we are already familiar with. So it's the scalar times the action of the operator on the original. Okay? So I have, and this is what makes it linear. Is equal to alpha so it's kind of obvious. Okay? I mean, it's almost obvious, but like I said, this course is one in which you begin with things that are obvious and end up with results that are completely non-obvious. Okay? Now, since I've been following this textbook strictly so far, I've been even trying to make the same mistakes as Shankar and same. But I find that there are certain points at which I can't do exactly the same thing. So, for example, he immediately begins talking about the action of operators on the bra. Sorry, the bra and the ket. This is the bra and the ket. This is ket. And then you have the bra form also. Bracket. And when we were talking about bras and kets earlier, what I said to you was that you can think of these two forms of the vector as kind of different avatars of the same thing. It turns out that it's not strictly true, okay? And the reason I need to add this additional confusion at this point is that next semester, or the semester after that, you will do a course on tensor analysis. And when you do a course on tensor analysis, you will also be introduced to the idea of the inner product once again. And when you're introduced to the idea of the inner product, you'll be told that when you find the inner product of the two vectors, you need something called a metric. Okay? And if you use that metric, essentially you have to you can use that metric to find a map between one form of a vector and its image in a dual space. Okay, you learn all these things. And so what we are really saying is that this is not a member of the same vector space, but it exists in a dual space. We'll not be concerned so much about those things in this course, but I just wanted you to keep that in mind because, and leave it out for the rest of this semester, because when you come to tensor analysis, the whole thing will be reintroduced in a different way, the idea of the inner product, using a metric. You'll be told that unless you define a metric, you can't have an inner product. So what have we done over here? How come we're living? So, just to keep that in mind, okay. So, it's not obvious that, if you put this over here, you'll be doing the same thing and so on. So, I'll come to that in a second. Let's first just think of linear operators and think of various kinds of linear operators. Then we'll go to the action of the operator on the bra. Okay. What is the simplest kind of operator that one can imagine? Absolutely. The identity operator. So you have an identity operator. Suppose I take an arbitrary vector from the vector space, I act on it with an operator, and I get the same vector back. Does that mean it's the identity operator? Think for a second. This is one of those traps that we physicists tend to fall into because we work from example. We don't believe in generalities so much. Just listen to what I'm saying, okay? If I take an arbitrary vector from the vector space, someone gives me an operator. I act on that vector with this operator, and I get the same vector back. Am I guaranteed that it's the identity operator? No. The identity operator is that operator which, when it acts on any vector in the vector space, gives me the same vector back. It's not that it's true for one, vector that it particularly likes, and it doesn't change that vector, it does other things to other vectors. Then it's not the identity operator. The identity operator is that vector, which, when it acts on any vector in this vector space, gives me the same vector back. And this identity operator is a vector on this vector space. Okay? So it has a particular structure in this vector space. So the identity operator in this vector space is not the identity operator in some other vectors. It's not even, these are different objects. Okay? The identity operator is defined on this vector space. So each vector space will have its own identity operator. Okay. Let's go a little further. Okay. Now, you want to figure out what an operator does to an arbitrary vector in a vector space. Okay. And you will want to do this for any vector. What should you do? Given that, you're not interested only in any vector in this vector space. What is it that we should think of next? What is the next idea that should come to our head?
Action of operator on these vectors.
Yeah. See, because you can write the vector, any vector in this vector space, as a linear combination of the basis vectors. So once you've chosen a set of basis vectors, and you've got this relation over here, and you can see that writing some arbitrary vector in terms of basis vectors is precisely that. So if it's an n-dimensional vector space, I'm going to be able to write this in terms of this. Okay. Basis vectors. And if I can figure out what this vector does to each basis vector, I have can figure out this action, then I'm home free. I mean, I've got the result. So this gives me, so I have so this is V. Okay. So essentially my job is to figure out how this, one of the fundamental tasks is to figure out how this operator acts on the basis vectors of the chosen basis. You might choose different bases, but the chosen basis, you figure out how this acts. Now, so far, I have not introduced the idea of an inner product in the context of operators. As I pointed out earlier, and I tried to emphasize this, an inner product does not come automatically with a vector space. You've got to add this to the structure of the vector space, and then it becomes an inner product space. But what we found was that when you added the additional concept of the inner product to a vector space, it began to acquire all kinds of new properties that were very useful. In particular, you could talk about something called orthogonality, okay, which is not meaningful unless you have an inner product. So once you have an orthogonality relationship, you can define a set of orthogonal basis vectors. And we found that a description of a vector in terms of orthogonal basis vectors is much nicer, much easier to work with than in terms of just an arbitrary set of linearly independent vectors. Though the basic idea, I must emphasize this, which you must not sort of confuse with the additional benefits that you get from orthogonality, is linear independence. Okay, so you should not assume, as I pointed out the other day, that whenever you have linear independence, you also have orthogonality coming along with it. That has to be added. You add it in further. Now, it turns out that because this discussion is much nicer in the context of orthogonal vectors, we will be discussing the structure of the operations of linear operators on vector spaces only for inner product spaces. We will not do it in general. And the reason for this is that, like I've said several times, this course is meant to be preparatory to quantum mechanics, and there you'll always be able to, almost all the time you'll be able to find a nice set of orthogonal vectors in terms of which to work. And those orthogonal vectors will also have other interesting properties. So we will work only for inner product spaces. And one of the reasons I never stick to one book is that, I'm a fault-finding person, as you all know by now. Okay, I begin to find faults with everything. So I read this chapter on Shankar, and he left out this very important point that from this point onwards, he was going to be working only with inner product spaces. He just assumed that because that was the last topic, more or less the last topic he did, he started getting these results. He said, how is he getting all these things? Then I figured that he was making the assumption that the basis was orthonormal. Whereas it's not necessary to discuss linear operators in the context of orthonormal basis. You can just use linear independence, discuss. The linear operators have nothing to do with orthonormal basis. It's just that the discussion is much nicer, cleaner, easier when you have an inner product space with an orthogonal relationship. Right? So I'm going to be doing that because that's what we really need. Okay, but for those of you who are interested, you can follow up in some mathematics textbook. I don't, even though I recommended this, I've given you the name of this book by Halmos, I don't immediately recommend that you start reading these mathematics books. So here's what I recommend. As we begin to advance a little bit, I'm going to give you a few more references and then you can begin looking them up. I found a really, really nice book. I don't want to give you the title right now because I don't want you sort of going around all over the place looking for these things. Let's get some basic picture in mind and then you can start exploring. Okay? I've also got from Dr. Vyas the title of the book that he uses, okay, since he's going to be teaching you quantum mechanics next semester. It would be useful to have his point of view as well. It's a mathematical physics textbook that's used in Harvard, and he sent me a PDF of that. It starts in a completely different way, okay, with some affine spaces and things like that. I couldn't even understand what the first chapter said. But, it's a more general way of doing things that connects to other things. Okay? Sometimes it's useful to have that as well, and I think later on it becomes simpler. So anyway, we'll start looking at various references right now, but like I said, when you do these things, it's important to be alert to the details. I don't know about your experience, but whenever I follow a single source and I sort of do one thing after the other, what happens is that my mind begins to close off and I don't see things very clearly. It's only when I give myself a bit of freedom that I begin to see the possible problems with this. So, by all means, follow the text that we are following, okay, Shankar, but, and use it respectfully, but not with a great deal of reverence. Okay? That should be your attitude in general towards all figures of authority. Teach, by all means, you respect them just as you would respect any other human beings, but don't be reverential towards whatever they say. Don't accept whatever I say, especially given that I'm teaching this course for the first time, as if I'm knowing the whole thing. Okay, I don't. There are a lot of things that I don't know, and we'll figure that out as we go along. And there are a lot of things that Shankar also doesn't do perfectly, but I think it's an adequate treatment of linear vector spaces for our purposes, and we'll stick to that for a while. Okay? Okay, let's write this idea down. Okay? Let's work out an example. first example that we thought of. So I have x, y, z, Euclidean space, okay. And let us call this our, we already have an orthonormal basis. So I'm going to work with an orthonormal basis, 2, and z hat, what you call ijk is 3. Okay. Now we want to do this exercise without recourse to the actual rotation matrix, which is the way we usually perform rotations. And so we're going to want to work with a particularly simple kind of rotation. Let us imagine a rotation about this axis, okay, by 90 degrees. And I'm going to call that r pi by 2 x. Okay. So this is rotation operator about x-axis. And we want to figure out the action of this operator on any arbitrary vector. So we want, in general, this but V can be written as alpha 1, 1 plus alpha 2, 2. This is just our fancy way of writing what you've been writing for years now, which is x, x hat plus y, y hat plus z, z hat. This is the fancy terminology for that. And I've written alphas because we've been using lowercase Greek letters to denote members of the field. And the action of this on this is therefore and so on. So we want to figure out what happens. So what happens when this rotation operator acts on the basis vector 1? Everyone can answer that question. Nothing happens. Because it's rotating about this axis. Nothing happens. So this is 1. But like I pointed out earlier, this does not make this operator the identity operator. Its favorite vector happens to be 1. When it acts on 1, it doesn't change it. Okay? But when it acts on 2, what happens? When it acts on 2, and this rotation is anti-clockwise. Do you say anti-clockwise or counterclockwise? Now, with the gradual Americanization of the world, I've noticed that people begin to say things like route and things like that nowadays. Whereas earlier we used to say route and they say Z instead of Z. We used to say Z. So when I went to the US, I found that people say counterclockwise there over there, whereas I grew up saying anti-clockwise, which is why. So suppose this operator acts on 2, what do I get? Everyone clear? This is 3. And this operator acts on 3. What do I get? This goes there. Now here's the deal. You now have everything you need to know about the action of this operator on any arbitrary vector in this vector space. Nothing more needs to be said. Okay? You might be one of those abstract-minded people who think it's below their dignity to write the components of a vector. They only want to work with abstract quantities. I have met such people. Okay? They only want to work with abstract vectors. They don't write, and they'll say things like, oh, it's the projection, maybe you're losing out. You're not losing out anything. Okay? It's like choosing a coordinate system from a problem. You have to choose a coordinate system. So you've chosen a coordinate system, so you work out. It's nice to be able to work everything out in terms of the abstract vector. And once you've got the action of the operator on a basis that spans the vector space, that's an important point. It has to span the vector space. Okay? You've got the entire story. If you have the action of the operator only on some of the basis vectors, then you don't have the whole story. Then you can't reconstruct the whole thing. If I know only this and this, then I'm not going to be able to figure out the action of the vector on an arbitrary vector in the vector space. But since this is a three-dimensional vector space, I've got three basis vectors which are linearly independent. Here we have the additional property that they're also orthogonal and normalized. Once I've got this story, nothing more needs to be said in some sense. Okay, everything is. So, just as we have, and what we're going to find is that just as we have a representation of these unit vectors in terms of columns. So this one is 1, 0, 0, and this one is 0, 1, 0, and this is 0, 0, 1. We will have a representation of the rotation vector in terms of a matrix. And if it's an n-dimensional vector space, what kind of matrix do we need? An n cross n. Okay, so now let's look at something that's going to be very, very important in quantum mechanics, which is the action of a product of two vectors. This is absolutely central to two operators on the same vector space. Otherwise, you can't talk about product or anything. So essentially, we're beginning to explore the first of the mathematical operations with operators. Okay. You've already seen this before because, when we were talking about the Taylor series in the very first lecture, we had e raised to the power of some differential operator. Okay, so you're already familiar with this. And in the first year mathematical physics course, we had e raised to the power of a matrix. So again, you're familiar with all those things. So you shouldn't be terribly surprised. You have powers of, so with that we can talk about something like, so I have two operators, omega and lambda, acting on some b. What does this mean? It means, by definition, this is how we define this. You let the one that is closest to this act on this. And I'm going to use, again, Shankar's notation. When this acts on this, let us say I have independent information. What happens is, this goes into another vector, and I'm going to denote that vector like this. Not to be confused with this. This line is separating. This means this is acting on this, and this is what has been produced as a result of this action. So this is, first you'll act on with that, and then you act with this. Now, the moment you begin talking about this product, you begin to ask yourself, what might happen if we perform the operations in the reverse order? And this is something that came up even when we were discussing operators in the context of differential equations in the second semester mathematical physics course. You may remember that when solving the harmonic oscillator equation and a couple of other equations of this kind, second order equation, what I did was I factorized the operator into two operators. Okay. Stopped in the middle of a sentence. Okay. All right, never mind. Let's